Okay, welcome everybody to the transportation seminar. Our guest today, my name is John Harvey. I'm with the Pavement Research Center and a professor of civil and environmental engineering. Today we're hosting Professor Elie Hajj from the University of Nevada, Reno. Elie's been doing some pretty sophisticated, amongst the most sophisticated stuff in asphalt pavement engineering, but that's not what he's going to talk about today. He's also doing a lot of work on, in the pavements world, we're trying to figure out both the material side and then keeping the infrastructure up to date. How do we minimize environmental impacts, energy impacts, and as well as the interaction of the pavement with the vehicles. So with that, I'm going to hand it over to Elie.
Thank you, John. Do you hear me in the back? No. How about now? Is that better? All right. Thank you very much for the opportunity to be here today. So my name is Elie Hajj. I'm an associate professor at the University of Nevada, Reno, of civil engineering. My talk today is about the new relationship models between the vehicle speed profile, roadway characteristics, pavement roughness, and vehicle operating costs. And I'll get a little bit into the details. What do we mean by vehicle operating costs? But before I start this, I just spend a couple slides to introduce my group. So I'm part of the Pavement Engineering and Science group at the university. Peter Sabali is the director, and we have another faculty, Adam Hand. He's also an associate professor. He's our research scientist. We do a lot of research similar to what John has been leading here for several years throughout the whole life cycle of the pavement. That you see that circle here and the different items. There's so many things that goes into a pavement life. And the core of our research and efforts has always been our graduate students that we truly appreciate. And these are our hardworking graduate students. We do have an AASHTO resource accredited lab in our facilities and in the different areas related to the materials, but also a few years ago we've expanded into full-scale pavement testing. We call it the Pave Box, and we just recently completed a study on super heavy load, and those are part of the experiment that you see over here where we've tested different type of buried utilities under dynamic loadings to see what the impact of million of pounds, if you want, on your existing buried utilities. With that, I would like to move on to the talk of the today. So basically, first I would like to acknowledge the Federal Highway Administrations for funding this project. It's been about 5 years, almost 5 years projects, very intense, but it was a lot of fun to work on this project. But at the same time, also, I would like to acknowledge the American Transportation Research Institute for their support as well throughout the study, because they've provided us with some valuable data related to the truck speed profile that they collect over time. In terms of the team that participated in this project, so this was basically a group effort. University of Nevada, Reno was leading that effort, and under UNR, basically, we have two major groups, our transportation groups that specializes in operations and simulations, but also we have our pavement groups, and there's basically Peter Sabali, myself, and our graduate students that really heavily worked on this project, Raimish Kaibain and Farzan Kazemi. They put a lot of effort and time into the developments of those models that I'm going to share with you today. Our partner was the NATC, the Nevada Automotive Test Center. If you're familiar with the West Track project, none of them has any of that. So back in about 2000s, there was there's a track where it's about 60 miles southeast of Reno, where they had automated trucks, right? So now we talk about autonomous vehicles and all of that. So 20 years ago, almost 20 years.
1996, 23 years
23 years ago. So that was there, okay? And those trucks, they were loaded basically, and they were going through, in circles. It's actually like an oval track, and it had different sections with different materials, different properties, and so on. And then over the years, you load it, and then you monitor the performance of your pavements. And that data turned out to be very valuable. It ended up in several studies, future studies. One of them is the CalME, the Performance-Related Specifications Project, the long life project that we see nowadays in California. So those same groups, apparently they're still there, and then they help us now, but in a different perspective, in this study to properly model the vehicle so that we can estimate vehicle operating costs, such as fuel consumptions, tire wear, your mileage-related depreciations, and so on. And then the last partner was our Dynatest Consulting, which is they specialize in non-destructive testing, like falling weight deflectometers and so on. So basically they have the expertise to go out into the field and measure the stiffness, the properties of the existing pavement, as well as the roughness of your existing pavement. So they can check how smooth is that ride for you and then provide us with that data. The overall objective of this project, basically to, the Federal Highway Administration uses the Highway Economic Requirement System software. They call it the HERS softwares. To estimate, actually to develop a report. They call the CNP report. They will submit to the Congress. It's a biannual report, but they do future forecasting related to improvements in transportations. And as part of those analyses, they do a benefit cost analysis. And then as part of the cost analysis comes the vehicle operating cost. The current relationships, actually, they were developed in 1982 by Zaniewski. And those relationships nowadays are dated because of changes in technology, vehicle technologies, big time, right? Now we have not only gasoline or diesel power, but we have hybrid electrics, other type of engines. And as well, the driving behavior. So the speed profiles, or what we call driving cycles, we need to have a better representations in our model when we do those predictions. So that was the main driving factors behind the studies. And we were tasked to update those models, the fuel economy models, updates what we call the non-fuel vehicle operating costs, which are the tire wear, oil consumptions, repair and maintenance, and your mileage-related depreciations. This sounds like fun, but if you think about it, all of these, they wanted to be factors of your driving behavior, your driving cycles. They wanted to be factor of your pavement roughness and the effect on the pavement roughness on your ride, function of the roadway characteristics such as grades, curvatures, and so on, and the type of the roadways. If you have full access control versus partial no access controls, number of lanes, and so on, if you have stopping lights, all of these, how are you going to consider them in your mileage-related depreciations, for example, right? So it's a very challenging aspect that we had to carry over the duration of the project. So there are three phases for the project, but the two main phases are phase one, to model the relationship between the vehicle speed and fuel economy. And for this, we had two groups, the full access control, we call them FAC, and the partial no access control, we call them PNAC. And then as part of that estimation, we had to take into account the speed, the grade, the speed limits, number of traffic control devices, and definitely for representative speed profiles. Then once we're done with this, the phase two was to come back and do the same work, but for non-fuel vehicle operating costs. So we kind of a little bit underestimated the effort. It's like, apparently it turned out to be multiplied by 3 at a minimum, but they were more challenging than the fuel consumptions. But also we wanted to introduce as well the effect of road curvatures and the effect of pavement roughness into those models. So what are the potential applications? While this study was heavily focused on the highway economic requirement systems, but basically because part of the HERS is your benefit cost analysis, and the benefit cost analysis is part of any life cycle cost assessment or life cycle cost analysis. You can make use of those informations. Or in terms of the pavement, we have the AASHTO Pavement ME the Ashton-Ware Pavement ME, where it predicts actually pavement roughness, and that pavement roughness can be used to calculate your vehicle operating costs as part of your life cycle cost analysis, and so on. So the applications are not really limited to the Hearst models, but it can be expanded to any other type of analyses. So starting with the major components of the study, our work was heavily based on what we call vehicle dynamic simulations. And I'm going to explain this a little bit what it means, but basically we're going to model the chassis of the vehicles, we're going to model the engine, and then eventually we're going to estimate the fuel burn and the fuel consumptions and any other type of parameters. And this requires the use of some of the software, and this is where our partner NATC is their major expertise. They're very heavily experienced in that area. This is really in a summary, the overall what we have done, right? There's a lot of effort that went into it, but if you think about it, every time you think about the vehicle simulations, you're talking about vehicle dynamics, right? And then as part of that, you need the driving cycles, because whatever vehicle you're simulating, you want to operate it over a certain speed versus time profile. So we needed to develop a database for driving cycles. And this is what we, mainly the UNR team undertook, and then did all the developments of the what we call driving cycles in our studies. Now, those driving cycles, along with the roadway conditions such as grade, curvature, pavement roughness, and so on, profile that goes into your vehicle dynamics models that has two components. One of them is the using the autonomy to model the engine and the drive lines, and the other one using the car sim and the truck sim. It's the same company, but they're two different software. One for regular vehicles, passenger cars, the other one for trucks, to model basically the chassis of the vehicles. And you combine them together, and then you get the fuel economy and any other type of vehicle dynamic responses, including, for instance, loading at the tires, right, due to the dynamic loads and your speed profiles, as simple as this. Driving cycles. Yes.
Oh, yeah. I was asking the driving cycles, did you get them from the
Well, I'm going to explain that right now. So the question was whether the driving cycles were guided from ATRI, and I'm going to explain the process over here, how the driving cycles were basically developed. So if you think about it, driving cycles, I don't know how many now we have in the room over here, 50s, let's say, 40s. If each one of them now, each one of us goes out and we drive the same roadways, and we collect the data of your speed profile, I'm sure we're going to end up with 40 different speed profiles. All right? So it's variable. It's there's your behaviors that comes into it, if you are an aggressive driver or not. So there's so many variables besides just the roadway characteristics. Plus, what time of the day you're driving that same roadways as well, it will influence your driving behaviors or your speed profile. So what we needed, remember, we're making this study is to be implemented on a national level. So we needed some kind of a representative driving cycles. So the first step for us was to collect second by second driving data. We didn't do the collections actually. Those were part of the NDS, the SHARP 2 naturalistic driving study, right, that actually covered 7 different states. And they had multiple trips throughout the day, throughout the month, and throughout an extended period, and for different vehicles, right, and for different distributions for the age of the drivers. Now, the data is huge, but as part, we had to make a request, and then we requested 4,400 trips. And every trip that we've requested, we wanted to be more than 20 miles, and with a certain characteristics in terms of, in urban, rurals, type of the roadways, and so on. So they had to write an algorithm for us that basically extract the data out of their main database. And we ended up eventually with about 7.5 million seconds of data. On the other side, they had video that were collected as part of that study. So we used the front video to predict or to assess the driving behaviors or the driving profile of the video on the front of the vehicle, the front vehicles. And that gave us another about 3.4 million or 3.5 million seconds of data. We coupled that with about 12.5 million of data for the Atri, because the Sharp 2 mainly were light trucks, small light duty vehicles, large light duty vehicles. We were missing the heavy trucks, right? Combination trucks and single unit trucks. So Atri helped us because they have a huge database. They monitor that on all of their fleet. But again, you cannot request all the data, right? You'll get probably 1 billion of seconds. And we don't want that. And they gave us a subset of their data. All that data get analyzed and filtered. But what we need to keep in mind that with all the data, we had all the roadway information database associated with it. So every second, we know where is that vehicle is, on what highway, how many, what's a grade, what's the curvatures, the location. So we have the roadway characteristics of the data. Using that information, we grouped them basically, if you think about it, in a matrix, right? We group them where within a certain characteristics, you have bins of acceleration versus bins of speeds. And then within those, we filled in the tables based on the likelihood of occurrence. What is the probability that you will be at this acceleration and this speeds? And based on that matrix, basically, we reproduce what we call synthetically optimized driving cycles that best represent that category. And that synthetically optimized driving cycles is based on the likelihood that the most likelihood is going to occur. The best representations of the population, if you want. And with this, it gave us actually different driving cycles, close to about 1,000 driving cycles. Here I'm showing you an example for a full access control. It was a curve A, horizontal curve, and a road grade C. And the speed limit on this roadway was 60 miles per hour. And I'm showing you here level of service A versus level of service B, D, and E. And you can see the difference, clearly the difference in the driving cycles, where you go from above the speed limit. We always observe that. So don't be surprised, okay? So that was very typical. But you can see that there is a slight variation in your speed. As you go to level of service B, there is still a slight variations, but it's very comparable to your A. The only difference at the different average speeds. But as you start moving to your level of service C, D, and E, and so on, you start seeing more the stop and go and a lot more fluctuation in your speeds. So if you think about the coefficient of variation of the speed, you definitely see an increase in your coefficient of variation. And think about if you're just measuring your fuel consumption at the average speed, you're going to be missing those fluctuations, your acceleration, deceleration, stop, idling, then go back. That's going to influence your fuel consumptions. So looking at those, we ended up with 920 unique synthetically optimized driving cycles. 320 were on full access control, and 600 driving cycles were on partial no access controls. Now, did we consider all the scenarios? Originally, we had our plan to consider them. Did we fill in all the gaps? No, right? Because even with the 12.5 million seconds and then 10 million seconds of data, that is still not enough, right? There's a lot of scenarios that might still need to be considered, but this is much bigger than any data that you can find right now related to the driving cycles. Typically, you'll find 6, 10, dozen, 20 maybe. We're talking here about close to about 1,000 unique driving cycles. Now, what do we do with those driving cycles? Well, we take those driving cycles, and then we want to be able to simulate them by operating vehicles on top of those driving cycles, right? So we ended up, eventually NATC built up for us 30 different vehicles. And then you can see them over here, from subcompact all the way to the 18-wheel truck, and then including buses. That was one of the major contributions that in a lot of the previous studies, buses like city buses, school buses, and so on were kind of left out. We introduced them in this study, and you can see the variables over here. Those 30 vehicles, there's 20 unique chassis, and some of those chassis had like 2 different engine types, let's say gasoline versus diesel. but also we consider the E85 fuel, we consider hybrid electric and LNG, basically to try to bring in the new technologies. And that's one of the reasons why the old studies don't have these technologies that built into it. And this is the beauty of the vehicle dynamic simulation, that now that those models are built in, you can change the technology. It can adapt easily to new emerging technologies. Now, so we have 30 vehicles. We have 920 driving cycles, right? You can start multiplying. You have different scenarios in terms, first, smooth pavements, and then roads with multiple grades, A all the way to F, upgrades, A all the way down to F, downgrades. You have also different curvatures from A to F as well. And then you have different roughness levels, okay? You put all of that together, it's over 52,000 simulations. Now, luckily now with the computers and all of that, this made it easier, but still is a lot of simulations. And what if you figure out you did the, we do them by batches, and then you figure out you made a mistake, you go and you repeat 1,000 simulations because it was only just one batch, right? Now, what are the pavement roughness levels that we've considered in the studies? So, we've considered 5 different levels, well actually 6 different levels. Good, and here are the units in meter per kilometers. The ranges, under fair we broke it down into 2 levels, and under poor we broke it into 4 different levels. So what happens, we develop pavement condition adjustment factors for each one of those levels. And there's a good reason for that, and I'll talk a little bit about it further when we get into the pavement roughness. So if you think about it, you have a physics-based model. We feed into it a given driving cycle, synthetically optimized driving cycles. We feed into it the road characteristics such as the grade, the curvatures, the rolling resistance, and so on, and the profile, right? Your roadway profile, which is the elevation as a function of time. And then we run it, operate it over that driving cycles, we get the fuel burns. And once you have the fuel burns, we can calculate the fuel economies. But also we get all the vehicle dynamics, the slip energy at the tire levels, any other forces, we can get them, and then we will kind of use them later on in our vehicle operating cost estimations. So starting with the model, to show you a little bit some of those models that were developed, starting with the fuel economy models, you'll see on the left-hand side a summary of the factors that are considered in those models. So those 52,000 simulations, right, eventually to make them implementable, we had to come up with some kind of nonlinear multi-regression analysis so that it can be easily implemented into HERS or any other type of softwares. Nonetheless, 52,000 simulations, you can easily do some kind of an artificial neural networks or, machine learning type of analysis to be able to predict, but within the limitation of those projects, the best approach was to develop equations that can be used. What does those equations consider? Here are the different factors, for instance, for the fuel economy. Vehicle type and characteristics, average speed, the grade, the level of service, the speed limit, number of traffic control devices, degrees of curvatures, and the roughness in terms of the power spectral density. The difference between the hollow and the solid lines, whether this variable was considered explicitly or implicitly. Okay? Very good. So starting with the fuel economy prediction models for straight roadways and smooth pavements. So that was our baseline, right? And then we start applying adjustment factors to consider roughness, to consider curvatures, and so on. Here's an example for a large sedan, gasoline powered. I'm showing you on the left-hand side, it's for grade A. On the right-hand side is for grade B. First of all, there are two on each one side, there are 2 graphs. The red one is what we call it the steady state analysis. What the steady state analysis is, we've conducted the same, the vehicles, instead of operating over the speed profile, which varies, we operated through just a constant speed. That's what the steady state. So this is your envelope, right? Now, the green line is the model that we've predicted. So basically, I can There is multiple points over here, and this is for a given prediction for a given set of inputs. So the green one take into consideration your driving cycles, which means takes into consideration what? The change in the speed profile, the coefficient of variation, if you want, in your speeds. Looking at the grade effect, you definitely see that your fuel economy drops when you look at the right versus the left, right? Which is obvious. You're going from a grade B to a grade A. That's what you kind of expect. Then within a certain plot, I'm going to show you some data over here. So assume that you are driving at 50 miles per hour, okay? And you hit, so you're cruising, there is some variation in your speed. That's why you see a little bit slight difference between your constant speed. But imagine now you get to a point there's congestions, right? Now, if there's congestions and there's a lot of stop and go and all of that, your fuel economy drops to about 21.1 miles per gallon, which is pretty significant, right? So that congestion could be, for instance, getting through a work zone. Right? And there's a queue, and then you have to stop, you have to go, and then stop further, and then accelerate a little bit further, then decelerate, and so on. Then you have a significant decrease in your fuel economy. But let's say you manage that you go through a work zone, but you keep on cruising, right, at a constant speed. Then your fuel economy is about 29.9 miles per gallon. All right? So there's a big difference between driving at a constant speed versus driving, with fluctuations in your speed profile. And you can see it as well over here. And then typically there's an optimum, right? That optimum is large, but don't you think if you're driving at a higher speed, you're going to save fuel economy? No, you're going to save time probably. You'll get faster, but you're going to invest more, okay? Because your fuel economy will drop. Yes?
So the dip in the constant speed, that's the gear change?
That's a gear change, exactly. So you see a lot of those. Sometimes there are two peaks in all of this because you're driving at a constant speed, so sometimes there's a gear change that occurs as part of the vehicle simulations. Now, the example that I showed you before was for full access control, which means there's no traffic signals, no stop signs, and all of that. We have another set of models now when you have such things, and we call the variables is NTCD, number of traffic control devices. This is basically how many, on average, control devices you have per mile. And what I'm showing you here an example between, for example, no traffic control devices versus 4 traffic control devices on the right-hand side. And at the same speed, you'll see that, and for the same speed limit, you'll see that when you have 4 traffic control devices, for instance here, it drops from 37.4 to 34 miles per gallon, right? But also what's important about this exercise, not only how many traffic control devices you have, but what is your average speed relative to the speed limit, right? So for instance, those different lines over here start with a speed limit of 20, okay, which is basically the top one, all the way down to the speed limit of 60. So if you're driving at 20 miles per hour at a roadway with a speed limit of 20, your fuel efficiency is better than driving at 20 miles per hour on a roadway with a speed limit of 60 miles per hour because you have more fluctuations in your speed profile. So that's also built into the equations or the analysis that were conducted. Now, what about the effect of road curvatures? This is very interesting because in the past, when we looked at the literatures, a lot of time the effect of grade on the road curvature was neglected. And what we find out in our simulations and verifications that there's an interaction between grade and curvatures. And here's, for example, for the same vehicles, for grade A versus grade B, this is how much you have reduction in your fuel economy based on the degrees of curvature. So the increase in curvature go this way, you have more increase in, or a higher decrease in your fuel economy. But if you're driving at a road grade B, you still have the same trends, but almost they are half of what you observe at grade A. So there's a large interaction between grade and curvature that cannot be neglected. Now, what about the pavement roughness? So for every vehicle, we we use the power spectral densities of a database of IRI data. So the Dynatest, our partners, they have a good database for, they've collected through the states. California is one of them, right? So they shared that data with us, and we have the elevation profiles for different roadways. And then for those elevation profiles, we developed a database of power spectral densities, and then we grouped them within those IRI levels. And within each level, we selected a representative PSD function. And that PSD function, basically, the associated elevation profiles, goes into your vehicle simulations.
You might explain IRI.
All right, so the IRI basically is a index. It's an international roughness index. So any roadways right now, if you look at it, it has some waves into it, right? Those waves, what we call a roughness profile, that change in the elevations. Now, to unify it, internationally, and to have like one number that will indicate how rough versus how smooth that pavement is, we convert that into what we call IRI. And somehow it's cumulatively how much you're deviating from a smooth plane, if you think about it. You sum it up. The higher the IRI, that means you're deviating a lot. It's supposed to be rough. The lower the IRI, that means it's a smoother pavement. Now, the problem with the IRI, while it's a very good index, the issue with it, we can have 10 or 1,000 different profiles that have the same IRI but have a significant different elevations. And to overcome that issues, basically we take that elevation in a time domain, if you think about it, and we convert it into some kind of a frequency domain. And then we work with it in the frequency domain. And that's how it basically gets implemented in the vehicle simulation models.
That's the PSD.
That's the PSD. I'm trying to put it in there. Yes. So once you do this, for every vehicles, we were able to come up with a pavement condition adjustment factors as a function of the average speed of the vehicle. And again, you see the different colors. Really, that adjustment factors, it doesn't start picking up until you are at around fair B. And then you can see sometimes it's about 2%, 1%, 2%, until very rough, you get to 4 and 5%. That's for one specific vehicle, right? Gasoline-powered subcompact vehicles. It changes, right? There's 30 different vehicles. There are 30 different charts like this developed for every vehicles. And here's a simple example at a given speed, degrees of curvature, and grade. If you have a poor A pavement roughness, the smooth roadways will have 55.5 miles per gallon. If you have adjusted for roughness, it will be 55.1 miles per gallon, and then if you adjust it for curvatures, it dropped to 53.9 miles per gallon. Curvature has a significant impact on your fuel economy. Now, what about the non-fuel vehicle operating costs? So there are the tire wear models, there is the oil consumption models, mileage-related vehicle depreciations, and repair and maintenance. And if you think about it, for example, in the tire wear, we want it also for smooth, rough, and include the effect of curvatures. So here's another example that shows you how important is the driving cycle, the speed profile. Again, there's on the left-hand side is for the grade A, upgrade A versus upgrade B. And right now, definitely, you see a shift in the data. So grade will play a role in your tire wears, right? Because the distribution of the loads in the vehicle dynamics will change, for sure. But then also, if you focus within the same plot, this dotted lines, solid lines, these are the steady state. Remember, these are constant speed. You're cruising at a constant speed. These data are from the driving cycles, and this is kind of like a fit model, if you want. At the high speed, you start merging together, which basically expected because your driving cycle at high speed, the variation becomes minimal. But at the low speed, you deviate significantly. And this is the same thing, going through a congested area, going through work zones, right? You might be ending up with a tire wear. If you're cruising constant speed this, if not, you're going to be significantly higher. So you may end up changing your tires much earlier than you anticipated.
Just to clarify what when you say average tire wear, is that kind of like assuming that the wear is distributed evenly across all the tires on the vehicle?
Very good question. So the question is if the wear is equally distributed over all the tires. Some of them have 6 tires and more on the vehicles. The average, yes. So we calculated the individual tires, and then for the modeling, we went with the average tire wears for the entire vehicles. But a very good question. And this is the effect of curvature on the increase in tire wear, similar to the model that you've observed with the fuel economy. But again, grade and degrees of curvatures are influential when it comes to the tire wears. And these are the pavement condition adjustment factors for the tire wear, which are different than your pavement condition adjustment factor for the fuel economy. And you notice that the curves are a little bit different, okay, because the impact on the tire wear is different than the impact on your fuel consumption. Here's to give you an example, right, how much it's going to cost. Yes?
So are all tires considered the same when you modify?
So all the tires are on the same vehicles. We use the OEM, the original equipment manufacturers, criteria and specifications and data. And for the calibration of, so maybe I missed that, but I didn't say that, but every part of this, from fuel economy for straight roadways, on roughness, on curvatures, tire wear, and so on, they were verified against measured data, field measured data. Some of them that our team collected as part of the study, some of them based on published data. And once we are comfortable, with the estimated versus the measure, then we went and we start doing the parametric studies and then do multiple simulations. So a lot of the data came from either existing databases, or also NATC had a huge database for tire database. We relied on that a lot also for some of the characteristics of the tires. Now, I had that questions before, well, what if I use this tire type versus the other? Can you tell me? The vehicle dynamics models can tell you that, but we didn't include that in here. So I cannot tell you right now, but you change the tire characteristics, that's going to influence your fuel consumptions and other things that we considered in this study. So here's for a straight roadway, no curvature, just to tell you in terms of cost, because eventually all of these has to go into some benefit cost analysis. This is how much it costs you. $1 per 1,000 miles if you are on a good, less than 95 inch per mile roadway versus poor A roadway, right? This is per 1,000 miles. It might sound not much, right? Typical average vehicles, they drive about, nowadays 12,000 to 15,000 miles a year, right? But this is only you, right? If you're doing a study and there's a million and million of vehicles, that will add up. Dollar amount will go up significantly. What about the oil consumptions? Well, we used a model called the equivalent models, which basically relate the oil consumptions to the fuel economy. And that's actually the beauty of the model, because remember, our fuel economy is sensitive to all those variables, grade, curvature, roughness, and all of that. So any factor that comes out of, or any fuel economy as a result of those will translate into oil consumption. Then I was able to adjust my oil consumption for grade, curvature, fuel consumption, and all of that. And here's an example, for instance. Left-hand side for small light-duty vehicle, subcompact gasoline. Right-hand side, class 2 truck diesel. Okay? Purposely selected those so you can see the oil consumption is significantly different between the two. Right? This is one thing. Then each one of them has two parts for two different grades. And you can see also the impact of the grades on your oil consumptions. The oil consumptions basically was determined in terms of the oil change intervals. Right? So if the norm is every 10,000 miles, but because if I have rough roads or I'm driving, aggressively, I make a lot of stop and go and all of that, now I have to change every 8,000 miles or 7,000 miles. And the difference in that will be your cost. So look at this, for instance, at a given grade, you're driving at 20 miles per hour. This is with the driving cycles, right? The stop and go and all of that. If you didn't have any stop and go, basically your oil consumption would have been less. This is the cents per mile, how much you're paying, would have been less. But if you're driving at a higher speed in this case, would even be further less. Okay? If I had gone instead of 45 miles per hour, probably 70 miles per hour, it would have gone up again. Okay? Because remember how the fuel economy kind of peaks for a certain, within a certain range of speed and then drops. So this is again tells you cannot neglect, you cannot just do it function of speed, average speed. There's also the variations that comes from the driving cycles is very important. whether for congestions, work zones, whatever that is, stop signs, right? Control devices, this is very important. Now, this is my favorite part. Well, all of them are my favorite part, but this is one of the most challenging was, how would you determine if I'm driving my vehicle, it's the same vehicles, right, that you own right now, and you're driving it in the city rather than driving it, I don't know, in Reno, right? Then my mileage, and I'm putting the same number of miles, but the value of my vehicles in San Francisco is a couple thousand or $10,000 less than the value of my vehicles in Reno. There's no data like that. All right? So we looked and looked and looked. People speculate. They say, yeah, it should be because in San Francisco you're going to stop and go a lot, and you're putting more effort on the engine and all of that. In Reno, you're more relaxed. Okay, I'll buy their car from you from Reno. So how are you going to evaluate that? I'm going to, basically, we started with the available data online, valuation data, like Kelly Blue Book, Truck Blue Book. There's also Bus Blue Book. So if you were not familiar with that, I wasn't before that study. Apparently, there's several of these. But we collected that data, all right, and then we plotted that data, and we saw how that data varies. Now, all of these don't consider at all the location, traffic characteristics, pavement roughness, and nothing. All what they consider is basically here. Your initial depreciation, right, which is function of time. So even if you buy your vehicle now and you leave it in your garage, it's going to depreciate until it becomes a collector car, then you start making money out of it after 30 years or something. But it's going to depreciate with time. And then with the mileage, it basically starts depreciating. Okay? Now that depreciation with the mileage is also a function of your initial depreciation. You can see the rate change. So this is if I buy a brand new car, right, in 2018, and I start driving it, that's how it depreciates. If I buy a Chrysler 300 2014 model, right, this is now how it depreciates. So the rate is different. Now, when I looked at that, those that are not familiar with the pavement engineering, I looked at it and said, this is a sigmoidal function. First thing came to my mind, the way we test the asphalt mixtures and we fit the data, it's like dynamic modulus. And I said, well, this is pretty well, but it's a little more challenging because there's not only a horizontal shifting, but there's also a vertical shifting. So I took the asymmetric logistic models, and we fitted the non-symmetrical sigmoidal functions with all those variables that will describe the age of the vehicles. Instead of the asphalt engineering, we use frequency and time. This is mileage for me. It doesn't matter. And instead of stiffness, I use the depreciations. And then we came up with the non-symmetrical logistic model to estimate Kelly Blue Book. So now, if you want to pay me to estimate your vehicle depreciations, I'll do that, so don't worry about it. But that was very challenging. Now, what's good about it is we said, okay, how are we going to introduce, now that we modeled, how are we going to introduce the effect of roughness, curvature, grades, and all of that? Well, something came to mind. Well, if I'm thinking along shifting, if I'm saying that you're telling me that the same vehicle in San Francisco is worth less for the same mileage, let me revert that. I'm going to say, well, they're going to cost more, but with a shifted mileage. And then we said, okay, what's the shifting mileage? We introduced here a shifting for the mileage factor, which is your average lifetime mileage divided by your adjusted lifetime mileage. How do we get the adjusted lifetime mileage? Based on your oil consumption change intervals, which is function of your fuel economy, which is function of the grade, curvatures, blah, 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 and all of that. And that will allow us basically now to estimate, for example, look at that, mileage-related vehicle depreciation as a function of the average speed, as a function of what? The age of the vehicles. So this is for one age. This is typically, right now, when we did that study, the average age of the vehicles in the United States was about 11.6 years. That's why we use that value over here. And this is how they depreciate basically as a function of speed. But if it was younger, you see that it's not a horizontal, just a vertical shift, but it has a different slope. So all of these now allow us in a really innovative ways to bring in the roadway characteristic and the speed profile into mileage-related depreciations. Now the last one is the repair and maintenance cost, which is also very, very challenging I think NATC here, they did a great job as well to kind of, go a little bit outside the box. But basically, the way we thought about it is from our simulations, we do have slip energy data that represents more the effort on the engines and so on. So we have some kind of a distribution of the slip energies. And if I have those distributions for the different roadway characteristics and so on, can I tie it to a distribution of repair and maintenance costs? And that way, every time I have a change in the roadway characteristics or the speed profile, then my repair and maintenance costs will be adjusted. So we collected two separate data. One is the slip energy data. The other one is the repair and maintenance cost data from published information for a fleet of vehicles and so on. And we developed a relationship between the two, or a function between the two. It's a mathematical relationships where from my simulations, I can estimate what the slip energy is going to be for a given driving cycle, roadway, pavement roughness. I get the slip energy. I use that function. It tells me, okay, this is your estimated repair and maintenance cost. There are some good tools available online for repair and maintenance. We went and also we looked into them and we collected data. A lot of those tools available online, as you know, basically when you start using them so often, they block you. You have to stop and then come back and then do it because they think that you're hacking the system or something. And here's basically an example. Again, it illustrates how important is the speed and the speed variations. For the same speed limits, if you're driving at 20 miles per hour, right, and then versus you're driving at 60 miles per hour, then your cost per mile for the repair and maintenance goes from $0.06 or 6 cents to about 4 cents per mile. And again, imagine how much you can accumulate over time. This is also some other things. We had them into groups because your cost will change if your vehicles has less than 50,000 miles, 50 to about 100,000 miles, and then 100 to about like 150,000 miles and so on. So your cost also will be different. Yes? Very, very good question. So the question is about the air resistance and the temperature effect on the fuel consumption, all of those. Those were considered in the modeling, but for representative conditions. So we didn't do variations in the dragging forces. Okay? We didn't do variations in the temperatures and the effect of temperature on the tire, for example, right? So all of the analysis, because remember, this is a lot of efforts. So we did it at the baseline. Now, a follow-up to this, there was another task about, okay, how can we take those and implement them in, for example, truck size and weight software that FHWA uses. In that software, they have a variation of load, they have variation of drag resistance. So we illustrated for limited examples what's the impact on fuel economy when you change the drag forces. So we illustrated that for them, but it's not part of the entire simulations because then we'll go out of hand. But it's very important.
So I'm guessing, having struggled with similar data for the last 2 years, that what NATC did was, for the different temperatures at which it was verified, take out the temperature changes the air density, which changes the air drag. So they would have taken that.
Exactly.
They corrected.
As part of the verification, that was part of their verifications. They had on board also measurements for the torque, for the fuel. So they had a lot of measurements, and then they used that data to verify their models. And once they're good, then we use one set and said, these are the basis for the models. Okay, so in other words, we don't want to introduce another variable. We introduce another variable, you multiply this by 3, 4, and 5. Then none of these students would have graduated, and then probably I would have lost all my hair. So, overall, you may be questioning, relatively, we're talking to us about tire wear and all of this. That's not important. For me, what's important is fuel consumption, and this was going to be the most, out-of-pocket expenses. Well, this is to illustrate. This is an illustrative example. Those proportions I'm going to highlight, they will change, right? But we picked simple one, average speed 60 miles per hour on a speed limit 60 miles per hour. I want to make it, very simple. and grade 0, there's no grade, and then very smooth. So think about it, this is your dream scenarios. Even with that, you look at the distribution, about 52% of your cost is fuel consumption, and 48% is your non-fuel VOCs. So do not underestimate your non-fuel VOCs. The major parts of the non-fuel VOCs would be your repair and maintenance and the mileage-related depreciations. Then followed by the oil consumption, and the least was the tire wear. For this example, this vehicles and so on. So the bottom line here, do not underestimate the non-fuel VOCs, because most of the time we think fuel consumption is a major one, let's focus on that, but there is other components that are also very important that needs to be taken into consideration. I think with this, we're good on time. I was trying to conclude the presentations, but we can take, I think, more questions. Here's some photos from our, awesome students throughout the years and so on. And we'll open the floor for any additional questions. I'd like to highlight, if you are interested in some of those reports, they are going through, all of them, completed, submitted, but they're going through the 508 compliance review. And it will take a little bit of time before they get published publicly, but if you have an interest, you can email me or email Valentin Volov, who's the AOR on this project, and then we'll get permission to share that report with you. Thank you.
And then see if there's any questions.
So for your synthetic drive
Sorry,
cycle,
Elie, you might repeat the question for the folks.
Right.
Everybody sits in the back, so they can't
But
hear.
also online they cannot hear, that's why I was
That's also-
trying to repeat it.
yeah, so for your synthetic drive cycles, how closely did you, I don't know if you looked at this or not, but how closely did those kind of reflect real life driving conditions? Like, is that, I understand that you're kind of using it for something a little bit different here, and so they might not necessarily need to reflect real life driving. But more from a curiosity, like how did that sort of process, what did the other end look like?
Actually, they reflect real life very well, because actually they came from real life data, but they came for the most likelihood real life data. So all that database, when you have millions of seconds, and you want to develop out of it a synthetically optimized cycle, you say, what's the likelihood that I'm going to be driving this way? And that's what the synthetically optimized driving cycle is all about. And even if I take now the same data set and we rerun it, we might end up with a slightly different one, right? Because the way the algorithms basically work. And then the one advantage of the synthetically optimized, I can build in different lengths of those driving cycles. So we did a little bit of optimization, and we find out 300 seconds was where it kind of the error will be, kind of stabilized, and that's why you'll see most of the driving cycles are around that 300 seconds range. So they do reflect very well, right? But it's not a scenario. It reflects a category of conditions, if you want. Okay. And they reflect the most likelihood way that you're going to be driving. Okay? Now, what I mentioned before is when we started and we put all those groups, like you have grades, level of service, curvatures, different type of vehicles, and you start multiplying that, probably you come up with 10,000 different scenarios. We couldn't fill in all the boxes. So we were able to fill in about 1,000 of those boxes, basically, which is still a major improvements to any other studies. But what I'm saying, there's still more room to grow from here and use that process to, develop additional driving cycles for scenarios that we couldn't cover in here. Okay? One of the challenge why we couldn't, because when we request, for example, the Sharp NDS data, they cannot tell you. You tell them, okay, I need this, and then they say, I cannot tell you. I can pull out the data. I can put some condition in my algorithm when it searches, but I cannot guarantee it. Say, okay, that's fine. Say, but you have to pay me to do that. So you pay, you don't get the output, then there's no way back, right? Because it takes time to run the algorithm and do all of that. So we try as much, and also the more you put conditions, the charges will go up because the time also will go up to find those conditions. So you have to optimize it and you have to balance it.
So this was NATC. I've been 23 years ago. I was out there quite a bit.
We need to get you more often now too. We need West Track 2,
There we go.
version 2, right?
Yeah. They were validating, at of the modeling from the vehicle dynamics. The other big set of data that we've used previously is the study from Michigan State, which was steady speeds, 5 vehicles,
Right.
and focused on pavement
Roughness.
and also macro texture.
Right.
Any cross-checking? Was there a task in there to cross-check and
We didn't.
independent validation, basically?
Yes, we didn't cross-check. Well, let me rephrase. We did internally. We did internally some numbers and see, okay, here's what we're getting, and so on. But we didn't do a full validations with this because for us, when it comes to modeling or fuel economies, for us there are 3 different approaches. One of them is the mathematical approach, and the model approach, and the vehicle dynamics approach. So the mathematicals could be empirical or could be mathematical. And the HDM4 that's used in the Michigan study, that's the kind of more the mechanistic or oriented, if you want, modeling, the mathematical modelings. And that relies on established relationship based on physics. The vehicle simulation models is totally different. The difference between the two, the top one is you need extensive calibration every time there's changes in technology. The bottom one is you do limited verifications and then you have the model. You start running parametric studies. So there are differences in some of the assumptions, but the numbers were not that off, especially when it comes to the pavement roughness related to the fuel consumptions.
On electric vehicles?
That was actually, I was about to ask a question about this.
So I think we have the same question is how much different was all these impacts? And I saw you only had a hybrid.
Hybrid electric, yeah.
Any idea, because just shifting the gears, you can go 45 miles an hour in one gear and the other gear and the fuel mileage changes by 20%.
Right.
Were you able to track the shift to when I ran out of battery life and shifted to the gasoline? And within the electric phase, how sensitive were all these things? How much did things change?
Yeah, so related to the hybrid electrics, it was actually one of the most challenging in here because you have to get to the state of battery to an equilibrium and all of that. So there is a lot of work behind it before you get into the fuel consumptions. And the output from the hybrid electric vehicles that were modeled, basically the fuel economy was different than the fuel economy of the gasoline and the power. So we were able to capture that. And actually we were putting a paper together to show those differences. But does the, no.
So does the sensitivity change? All the curvature effects, the drive cycles, and the inefficiencies of the internal combustion engines and the drive cycles, how do some of your main takeaways for combustion engines, do they translate? Where are they similar? Where are they different for the electric?
They were different, but you have to keep in mind the same driving cycle was used for, right, yes.
So same driving
yes.
cycle, yeah.
So they were different. The outcomes were different.
Okay.
Yes.
Any particular way they were different?
No, we have the numbers, but not on top of my head. I mean, the fuel economy was higher on the hybrid electrics compared to the gasoline and the diesel power.
Say that again.
The fuel economy on the hybrid electric was higher than the gasoline and the other one.
So
But
one other question in your repair costs, one of the big issues in figuring out the net benefit of an electric vehicle, one of the biggest ones, how long does the battery last? And question we've been trying to figure out, and I don't know if you got there, but I think that's the next study, is
Right.
what does the roughness do to the battery?
To the batteries.
I know Paul Erickson, we've had Paul Erickson. So he said hydrogen fuel cells actually work better with a little bit of shaking.
Shaking.
How about the life of
Yeah.
batteries? Any thoughts from NATC?
We haven't discussed this. I'm sure they have some, more insight about this. This is the repair and maintenance cost. It was one of the most challenging because the data that's available, you see, like what you're saying, there's no data that really did, controlled studies.
Nobody's measured this.
measure this and then tell you, yes, here's the ratio and here's how much you save. There's nothing. Most of the data that you see over here when it comes to the cost is coming from aggregated data on the fleet vehicles and so on, and we had to rely on that. And the NCHRP 720, they did some repair and maintenance, but they only looked at the suspension fatigue. Here, no, they wanted everything, not only the fatigue and the suspension, so we had to be a little bit more innovative and go into the different approach. But we haven't got into, I mean, this is too detailed that we haven't got into it as part of this study at all.
Because we're approaching, what percentage are we electric vehicles now?
5?
8%?
Sales are of the active fleet.
Aggregate fleet. Sales are 8-ish. To hit the 2030 carbon goals, or do we have to be?
Roughly
Double, 6, 7%, or
double the sales. I don't
double
know
the
if
sales?
16% sales and 6-7%, and then to hit 2050?
it would have to be even more. Gil would know, he's not here. But.
Any other questions? I have one last question. I brought Elie so he could answer all my questions. Go ahead.
No, that's fine. That's okay. Sharp NDS and the ATRI for the trucks.
Okay, so
No, so the question whether there was a software to predict driving cycles. No, we didn't. We couldn't find, something that will give you a representative driving cycle. There are some availables in moves or the EPA cycles and all of that are availables. But again, if you look at those, they're probably there's a dozen or something, and they don't consider all, They're good for the purpose that are being used, but not for this study, for the purpose of this study. And this is where we had to rely on actual measured data, which is the ATRI and the Sharp NDS. And the challenge was how to take that data and then make out of it some representative driving cycles that can be used. And the algorithms to come up with those driving cycles, that was written in-house by our faculty, Hajj, from the traffic engineering. Oh, you have to ask him.
quick one. I thought you mentioned
Well, what we were trying to do as much as possible to make everybody aware of this work and then use them in LCA, LCCA, Ash to Wear Pavement ME.
So when we get to the end, that'll be sort of my summary point and question.
This is the whole purpose, to disseminate that as much as possible, because in our mind the application of this is broader than just what HRSC. It could be for different. But you have to set what are your basically needs, and then you may not end up using all the models available. You may end up pick only the pavement condition adjustment factors, or I don't know.
Elie, mine, first of all, is a clarification. Scenario cover both
Yes. So the question whether those scenarios cover urban and inter-urban, yes. So when we requested the data, urban versus rural were factors. The lengths of the number of traffic control devices that were factors. So yes.
any
Oh yeah, no, they're different. The models for the full access control are different than the partial no access control. But between urban and rural, we, at least I would say, based on the data that we had, we couldn't separate them. Okay? Now, because you may come back and say, oh no, we find out that it is different. But based on the database that we have, it didn't come out to be a significant variable that will allow us to separate it into urban versus rural.
Okay. So after the result that you obtain, let's say with ideal scenario, possibly this type of result would be an input for autonomous driving.
From what perspective? So the question is if these results could be an input for autonomous drivings. From what perspective?
Well, if you want to optimize, you're talking about costs, right?
Mm-hmm.
If you want to optimize the user costs, consider the driving cycles are actually
Part of it.
a big contributor.
Well, what comes to my mind, and plan properly when you want your move and all of that, then yes, you can save a lot on the cost. But if you're talking from a perspective, that's the thing. If you have a lane just for autonomous vehicles, right? That's assuming this was going to happen. Then your driving cycle probably is going to be different. Okay, but based on what I heard last AAPT, that we have a little bit the wrong assumptions that we think that is going to be more channelized, more smooth, but not necessarily between autonomous driving and our regular driving behaviors. We tend as well to brakes and get close, like those vehicles. They can get close to each other, and so I don't have the right answers. How would be the driving cycles for autonomous vehicles? But it's worthwhile looking at
So
that.
you could actually simulate an autonomous driver cycle, because that's software,
It can
and it senses something in the hard braking.
stop
does,
it, and then
and it depends on how they program that. Is it an
The ramp
assisted
up,
driver
yeah.
or not? But you could then run that through and check.
at least get theoretically what there will be an impact or not
Use that to optimize it.
as an input.
People have taken the LCA class or my question, we want to tie into this. In all of our LCA models, looking at pavement effects and the emissions from building a road and maintaining a road or bridge, and a bridge, and the savings, which are tiny per vehicle, but when you have lots of vehicles, it starts to be much bigger materials. One of our questions is, we have not brought in, we've only looked at the fuel effects. What we have not modeled, anybody doing LCA of vehicles? Okay, so one of our questions is, we've never brought into those models the effect of the infrastructure on not just the combustion emissions, but the emissions of using your tires faster, which is a very big environmental impact.
Yeah.
I know the country of Chile, the third largest environmental impact they have is the tire consumption. Hydroelectric. But bring in the environmental effects of the vehicle depreciation, replacement time, and all that
into the
oil,
yeah.
and the suspension parts, and the emissions models for all of those. I
That's
think that's the tie-in.
this is a bigger picture, actually, much bigger. It's a system.
System expansion.
Yes.
Beyond just the fuel.
Oh yeah, definitely. And then
Anybody working on any of those questions? On the edges of it, maybe.
Yeah, we're kind of like, we're tiptoeing around looking at a hazy project without well-defined borders yet.
Anybody working on LCA of fuels? Anybody working on fuels? All right, do we have any other questions? Party's over outside, so forget about it.
so forget.
All right, thank you.
Thank you.